This video is by Justice and Mercy Energy Services. It's about voltage.
All right, this next video is about voltage. One of the things we need to learn how to do is speak good electricity, to quote our former professor, Don Ferris, who used to be at Baylor. We need to understand that electricity are the terms of electric circuits, and voltage is one of those. Voltage always exists between 2 points. It's a very common mistake to say, well, the voltage flows here or the voltage flows there. No, the voltage doesn't flow. The voltage always exists across an expanse between 2 points. The volt, 1 volt, then is equal to 1 joule of energy per 1 coulomb of charge. So here I've drawn a big collection of positive charge and a collection of negative charge, and those are going to be attracted to each other. Now we're not going to talk about the details of that equation, but positive and negative charges attract, and they're going to attract a lot. Holding these charges apart will require a force. If I spend energy applying that force over some distance, some separation distance, then moving them closer together or farther apart, I've expended a force over a distance, and that is what we call work. Work has units of energy. Or more precisely, work and energy have the same units. So a newton is a force, a distance is a meter. A newton meter then is a unit of work or a unit of energy, as is a foot pound. A foot is a unit of distance, a pound is a unit of force. Okay, the units of voltage are 1 volt is equal to 1 joule of energy per coulomb charge. So energy per unit charge. Perhaps a helpful way to think about this is about potential energy, because we're very familiar with potential energy, not necessarily electrical energy. Potential energy of a raised mass is mgh, mass times gravity times the height it's raised from. Now the mass times gravity is equal to its weight. And I've got here a couple gallons of water. Now water weighs about 8 pounds per gallon. So mg, the mass times gravity, is about 8 pounds for a gallon of water. And if I have it up here on this ledge, then it has a certain amount of potential energy relative to if I put it on the floor. If I put it on the ground level, it has 0 energy relative to the ground level. But again, that's got to be in comparison to some reference. We've got to have some external reference to measure our energy from. And in this case, it's the floor of the parking garage here. But I could use a different reference. I could throw the jug off of the 4th floor of the parking garage, and then it has a different amount of energy because it has a different reference point. Like in this example here. And voltage is not just energy, but it's energy per unit charge. So you could kind of think about it like energy per gallon. The total energy is doubled if I have 2 gallons instead of 1. But the energy per unit gallon, which is our voltage analogy, that doesn't change it. Let's look at a 9-volt battery. What does a 9-volt battery do? What does it mean to have 9 volts? So here's a little 9-volt battery like you might find in a smoke alarm, for example. And they're often labeled with the positive on one terminal. Now, the positive terminal is, what that means is the charge, any charge, in fact, every coulomb of charge, I didn't write the word coulomb here, but I should have. Every coulomb of charge on this side has 9 joules of energy more than something else. And that something else is the other side, the minus side. The minus side becomes the reference. And so, so we're talking about a relative energy level here between the plus and the minus side. The plus side is the high energy side, the minus side is the low energy side. So we typically use the negative polarity to be our reference, and that means the low energy side. And that means remember, every coulomb of charge then has 9 joules of energy more than it did at the negative side. So it's a way of increasing the energy of a coulomb of charge. We could have used H and L example, for example, instead of for high and low energy instead of plus and minus if we wanted to. Okay, now let's imagine you take a couple of 9-volt batteries and we put them in a configuration like this. By the way, you can actually do this, and there's some crazy people on YouTube that have put these together in such arrays that they've created thousands of volts. It's kind of entertaining, but rather dangerous. So if you connect the negative of one to the positive of another, like I've done here, see how the three are plus to minus, then we get actually an addition of energy, because the energy is the same whenever 2 points are connected between a conductor. Okay, and so what we're saying, well, the question is, how much energy does each coulomb of charge have relative to the other side, and the other side being the unconnected terminal? So A battery on the minus side is our reference, C battery with the plus is our positive, and note that the positive terminal of A and the negative terminal of B are connected together. They have the same energy. So if we were to move from the negative terminal of A to the positive terminal of C, we would go up 3 sets of 9. In other words, 9 joules at a time as we move from one battery to another. When we leave battery A, we begin battery B, we pick up another 9 joules. And then as we leave battery B and move to C, we pick up another 9 joules. Okay? So just like current, by the way, current has to be specified with an arrow and a magnitude, such as current I on the right. I'm sorry, it clipped off a little bit there. Or current 2 amps, as I've shown here. Voltage must also be expressed with its polarity showing. So these two parameters then become sort of the magnitude of the voltage and its polarity, P-O-L-A-R-I-T-Y, polarity. Which poles? In other words, which one's positive, which one's negative? Sort of like the polarity of the Earth, the North Pole, the South Pole. So I'll draw a couple of examples here on some fictitious electric components that we might have. These components, then they're going to have a positive side and a negative side in their voltage expression, and also some kind of value. In this case, I'll put the value as V. V is a variable, V volts. I don't know how many volts it is. It's an unknown we might have to solve for. Or I might have a 3-volt drop across a certain component. And but always I'm going to have to show the positive and negative polarity and also the value. That value also might be a negative value, positive and negative as shown on the third example here, and the value is negative 6 volts. So one thing about this, if I have a negative value, or even if I have a positive value, I can always flip it around, flip the polarity around, and pick up a negative sign. So if I change the plus and minus on these two, then you notice I changed the minus 6 volts to plus 6 volts. Okay, so I can go back and forth with that. That's a nice little trick that we can use for solving problems. Likewise, something I failed to remind you of during the current video is I could do the same thing with current. If I have current flowing one direction, I can redraw that current flowing the opposite direction if I change the value by multiplying it by -1. So the 2 amps to the right is equal to negative 2 amps to the left.
Justice and Mercy Energy Services, we design, install, and maintain solar energy systems in Haiti to combat energy poverty and create jobs. Check out our website, make a donation. Thank you.